observe this quantity, this VR, okay, this we can take it as VC cos theta, and we can take it as VC cos omega t. You replace theta by omega t, right? And the orbit has a time period which is given by p orbit. It is given by 2 pi upon omega. So this has got nothing to do with mechanics. This is just mathematics in circles. Okay. From the center of mass, we should come to know that m1 r1 is equal to m2 r2. So from here immediately it will follow that P1 is equal to P2. So now what do you mean by 1 and 2? 1 and 2 are the two bodies which are gravitationally bound. We are talking about a binary star systems, though, so they correspond to the properties, the physical parameters of the two independent stars. But we can use the same mathematics for any bound system. It can be a star and a planet system. It can be a planet and a satellite system. Okay. So then we just have to be very careful about using which body is 1 and which body is 2. But when they are moving around their common center of mass, they will move with a common periodicity. Now, P1 is equal to P2 and P is given by 2 pi r upon V, where you can replace omega by V by R. Okay. Then immediately if you for taking for the two objects 1 and 2, you see that R1 upon V1 is equal to R2 upon V2. And hence, you come to this very interesting relation which says M1 V1 is equal to M2 V2. This might give you the impression that the linear momentum is conserved, but that is not exactly the case. It is just a mathematical truism. Okay. So when we talk about M1 V1 equal to M2 V2, it is very useful relation when it comes to solving problems. But please don't develop the misconception that in this system the linear momentum is conserved. No, we are not talking about linear momentum at all. What is conserved is the angular momentum, and that leads to my P1 equal to P2. Now, this portion is just a consequence of the conservation of angular momentum. Now we introduce Newton's laws of motion, because the two bodies which are gravitationally bound to each other are exerting gravitational force on each other. So now it is a balanced system, it is a bound system. So the force of gravity is m1 m2 upon r1 plus r2 whole squared. Okay, and because it is a balanced system, the forces acting on them are exactly the same. Okay, that is the gravitational force is the same. Whenever an object is moving in a circular path, it has to experience a centripetal force. It is the centripetal force that causes its change of direction of motion continuously. The centripetal acceleration is causing it to accelerate continuously. So please understand, a body which is moving in a circular orbit is actually moving under a force all the time. It is accelerating all the time, and that acceleration is manifested in its change of direction. And this centripetal force is not a physical force. The physical force is caused by, in this particular case, gravity. There's always a physical source that will cause the centripetal force. Please understand this very carefully. If I tie a stone at the end of a string and I move it, hold it and move it in a circular path, it is the tension of the string that provides the centripetal force. Here, the two bodies are moving around due to gravity. The gravity is providing the centripetal force. Without any physical origin of the force, you will not have a centripetal force. Now, the centripetal force is mv squared upon r. Considering the first object, this is my expression for the centripetal force experienced by the first object. Okay. Now, as I said that Fg is equal to Fc, so G m1 m2 upon r1 plus r2 whole squared is m1 v1 squared upon r. Okay. This is the most important relation that you need to understand. Once you understand this, then you know that Of course, this is a mathematical derivation, and also we see that V1 is equal to 2 pi R1 upon P, where P is the time period which is very easily measured. Mind you, when we are looking at any change which is periodic, it is easiest to measure the time period of the change. Okay. So once we know the time period, then we can write the velocity in terms of the R1 and P, and hence I can derive this relation where 4 pi squared R1 upon P squared is equal to G m upon R1 plus R2 whole square. Okay. Mind you, this side M2 is there, although I am measuring R1. Okay. That is because the mass M1 has cancelled out. Okay. So this is a very important relation. Now, it might happen that you have an estimate of R1 plus R2. Okay. And it might happen you don't have a very good estimate of R1, but you have, from this measurement you get an estimate what R1 order of magnitude can be like, and then we can keep on improving our observations, doing multiple observations and fit the data and get an estimate of R1 and R2. Okay. And of course, if we measure R1 and R2, then we have a handle on measuring M2. So understand, all these measurements are an iterative process. You make an estimate, then you move ahead, make a better estimate, and then the better estimate value is put in the previous equation. So, if we replace capital R equal to R1 plus R2, this is the separation of the two bodies. Again, I'll repeat, if it is circular, it remains constant. Otherwise, this particular quantity will change as a function of time. Then you just do the mathematical jugglery, take R1 out, and then from a previous relation, we know the relation between R2 upon R1 can be M1 upon M2, because M1 R1 is equal to M2 R2. And hence, what you have out here, you can write this separation in terms of the masses. This is extremely important, because it can happen that you are able to do the spectroscopic study, you are able to measure the temperature of the star, and from the HR diagram, you are able to measure the luminosity and hence get an estimate of the mass depending on the spectral classification. So now it is an independent observation of spectrum that gives you the mass, and hence you can get the value of R1 if you measure the separation of the. So this is a very crucial step in our understanding of the gravitationally bound systems, and hence from the measurement of R and the masses, I can get the separation of the object from the center of mass. Now, this is a relation that we had derived in the previous slide. So once we take this relation and take this relation, we get a very important relation. Okay, this is the most important relation, mathematical relation, that we will use in gravitationally bound system, because we have measured the separation, assuming you have measured the separation between the objects M1 and M2. And if you know what M1 and M2 are like, what the orders of magnitude at least are like, and periodicity is something that we can mention, we can measure very easily, then you have classified the system. Okay. You know now what R is, what M1 and M2 is. And as I said, using this value, you can go back to this relation or this relation, and iteratively, you get better estimates of your masses and the radii. Now, this relation, you have to be very careful when you are doing a measurement. What unit are you using? Because the SI unit or the CGS unit can become very cumbersome and not give us a good visual feel of the relation. So, more often than not, you write this relation in terms of you talk about R in terms of the astronomical unit, which is the average distance from the Earth to the Sun. You measure the masses of the stars in solar unit, and you measure the periodicity in terms of years. But mind you, immediately when you look at this, you should realize that this relation, this kind of units is very useful when you're talking about a wide binary system. Nowadays, if you go to the cutting edge understanding, we have many binary systems which are extremely close. And if I remember correctly, the closest binary system has a periodicity of few tens of minutes. So in that case, this unit is not going to be useful at all. But if you look at the traditional astronomical data, then that is when this unit has been very, very useful. And of course, from the definition of angle, you know that the R, that you see the separation of the two objects in the sky, is a function of the distance and the angular separation. So this relation gives you the measure of the distance in terms of linear scale, and what you measure in the sky is the angular scale, and this distance you can measure from the luminosity of the star and make use of the HR diagram. Okay, whatever flux you measure, you do the spectral classification, you understand what the luminosity should be like, and hence from the measured flux and obtaining the luminosity from the HR diagram, you can get the value of the distance. Now, when it comes to the unresolved binaries, okay, so far we were talking about the mathematical formalism which is very, very useful for resolved binary star systems, where you can measure the masses of the individual stars. Now, let's look at the case where you do not measure the mass of one star and you can measure the other star. So, what do? You take R PV upon 2 pi. This is a generic relation of any circular motion. R1 plus R2 is your capital R, the separation, where R1 and R2 are the distance of the individual object from the center of mass. And hence, this R you can write as P upon 2 pi into V1 plus V2, the two objects which are going around. Okay. And then we use the same relation which we have used beforehand, and then come to the conclusion. Look at this part, this equation we will deal with later. Okay. Here, when you look at it, it is M1 plus M2 is equal to P V1 plus V2 whole cube upon 2 pi G. P is a measured quantity, G is universal constant. Here, you have to infer V1 and V2. Now, V1 and V2 are inferred only if you can measure the spectrum. Okay, otherwise we will say this is unresolved. We do not know the properties of the system. When you know the velocities from the spectral measurement, then you have a handle on M1 and M2. And since you have already observed one particular star, say M1 or M2, and you know the classification from the spectral classification and HR diagram, then you know the mass of one, then you can infer the mass of the other. So this, forget this for the time being, this is the important relation which you use when it comes to finding the mass of an unresolved binary star system. When your binary plane is not inclined to your line of sight, it is inclined at an angle of I, which we will cover later, then this relation has to have this component of sine cube I. Okay, this is very important when we talk about angle of inclination. Okay, now we already saw that M1 V1 is equal to M2 V2. Okay, then if we can measure V1 and V2, then immediately we get a ratio M1 and M2, and hence we have now two equations with two unknowns. Okay, suppose M1 and M2 are not known, but you can measure V1 and V2. Then take this equation, take this equation. Two equations, two unknowns, so you can solve them. Okay, and if we can measure the masses, then obviously we can solve the velocities. Maybe we take a break here.